Continuing with our notes, we have three related questions. I to the fifth, I to the 101st, I to the 102nd. These are all pretty similar questions, and even the last one will eventually connect to these other three. But the idea behind these questions is we have to pull out as many I squareds out of the expression that we can, because every I squared equals -1. So in a circumstance like I to the fifth, I want to rethink this as I squared times I squared times I to the first. And because, first of all, this does indeed equal I to the fifth, because when I'm multiplying like bases from our rules of exponents, we're just going to add up those exponents. So 2 plus 2 plus 1 equals 5, so I to the fifth. And so by rethinking this expression, this I to the fifth, this way, I can see that I've got a -1 times another -1 times just an I to the first, which is root -1, but we're going to leave it as I. And so then I've got -1 times -1, which is 1. 1 times I is I. So I can simplify I to the fifth down to just being I. So I always want to remove any I squareds, turn those into -1s, and then the highest exponent of I should ever have in a final answer is 1, I to the first. If we take I to the 101st, writing it out as we did here would take a while. So we need a shortcut for that. So my advice is to take the exponent and divide it by 2. So if I take I to the 101st, if I take 101 divided by 2, I'm going to get 101 divided by 2 is going to be 50 with a remainder of 1. So that means I'm going to have 50 I squareds. So if I think of my exponent rules, power to a power, I multiply, so that would be 100 i's right there, I to the 100th, but I need 101, so that means I've got one extra I left over. That's my remainder that I see here. And so now I squared can be rewritten as -1 to the 50th power times I. And so then, of course, if I'm multiplying by a negative an even number of times, that's going to equal a positive. So it's just going to be +1 times I, which gives us just I again. For I to the 102nd, if we take that same approach, so again, take 102 and divide it by 2. So that goes in evenly this time. It equals 51. So that means I'm looking at I to the 50, or I squared to the 51st. Well, again, that's -1 to the 51st power. I squared is -1. So now I'm multiplying -1 times itself an odd number of times. So my result here is going to be -1, and since I had no leftover i's, it's just -1 is my answer. And so we can again apply the same idea to this last question. So in the last one that we see here, first of all, we have a negative times a negative times a negative, so I'm going to end up with a negative, at least temporarily. We're going to multiply the numbers. 8 times 2, 16, and then I've got I times I times I to the fifth, so I've got a grand total of 7I, so I to the 7th, just adding up the exponents on those. And so now I'm going to do the same thing as I've done on the others. I have to remove as many I squareds as I have. So I'm going to have -16. So if I go 7 divided by 2, that goes in 3 with the remainder of 1. So that means I have 3 I squareds. So that's 6 i's times the one more to make I to the 7th. And so now I've got -16 times -1 to the third, I squared is -1, times I. Well, -1 to the third power, negative times negative times negative is going to be a negative. So I've got -16 times -1 times I. So -16 times -1 is positive, so we end up with a result of 16I. So the bottom line is, for these 4 examples, is we have to replace all of the I squareds that are embedded in the question with -1s. And so our best approach is to just take the exponent on the I, divide it by 2. If we have no remainder, then we just have I squared raised to that exponent. If we have a remainder of 1, then that just means we're going to have an extra I left over in our answer. Now, just like we saw with regular square roots, we had conjugate pairs, so like 5 plus root 3, its conjugate pair was 5 minus root 3, and this was useful for us when trying to rationalize a denominator, make the denominator not have a square root in it. Complex numbers also have conjugates. So if I have a plus bi, then its conjugate is going to be a minus bi. Or in other words, the real part is going to stay the same, it's going to be unchanged, the imaginary part will just change to its opposite. And so where these conjugates are going to come in handy is in an example like the third one here, because we're not allowed to leave I in the denominator, because I, if you'll recall, is root -1, so I can't have a square root in the denominator, so I'm going to have to use conjugates to help clear that out. But we'll get to that in the third example in just a moment. In the first example that we see here, we're just going to FOIL like we would if I was x or y or some other variable. And then again, remembering that if we see any I squareds, we have to convert those to -1s. So using our FOIL technique, we have 6 times 4 is 24. We have the outer 6 times 2i gives us 12i. We have the inner -2i times 4 is -8i. And then finally, we have -2i times +2i. It's going to be -4i squared. So I've got 24 plus, I've got my like terms in the middle here, 12i minus 8i is 4i. And then again, this I squared is going to turn into -1, so it's going to be minus 4 times -1. So that's going to become plus 4, so 24 plus 4i plus 4, and so then we get a final result of 28 plus 4i. So we just use our regular FOIL techniques. We treat I as if it's just a regular variable for all of that work. It's just at the end, after we've done the FOIL, that we have to treat that I squared as a -1 and then simplify our expression that way. And then we write our answer in this a plus bi format, with the real part first and the imaginary part coming second. For the middle one here, our standard FOIL rules apply. We cannot just square the individual pieces. We of course have to rewrite this as 1 minus I times 1 minus I and use our FOIL technique. So we've got our firsts, 1 times 1 is 1. Our outer and inner are both the same. We have a -I times 1, we have another -I times 1, so that's going to give us a -2i. And then finally, -I times -I is going to be positive I squared. Now, of course, at this point, the I squared gets switched into -1. So now we've got 1 plus -1, those cancel each other out. And so the result of squaring 1 minus I is just -2i. The last one is where we're now going to have to use those complex conjugates. So I can't simplify this expression. We've got the 1 minus 3i is linked by subtraction, same thing in the numerator. But I can't leave an I in the denominator because that represents a square root, root -1, and we're not allowed to have square roots in the denominator of a simplified expression. And so our only way to simplify this then is to multiply the top and bottom by 1 plus 3i. So again, our rule for conjugates is we leave the real part the same and switch the imaginary part to its opposite. So what that does for us is it sets up kind of a difference of squares pattern in the denominator. So we really only have to multiply the firsts and the lasts because the outer and inner terms are going to cancel each other out. So 1 times 1 gives us 1, and then we've got -3i times +3i. It's going to give us a -9i squared. And so we can see that we're not going to end up with an I in the denominator after we're done with this because those outer and inner terms cancel out. So we just have a real part, and then we have an I squared part, which is also going to end up being real. Up in the top, we do have to do our full FOIL. So I've got 6 times 1 is 6. My outer is 6 times 3i, so I'm going to get 18i. My inner getting a little crowded here, is negative 7i times 1, so minus 7i. And then my last is that negative 7i times 3i, so negative 21i squared. So up on the top, I'm going to simplify. I've got 6. 18i minus 7i is 11i. And then that minus 21i squared, that I squared is going to become negative 1. So negative 21 times negative 1 is going to be positive 21. And then on the denominator, I'm going to have the same sort of thing. I've got 1, and then it's negative 9 or minus 9 times that I squared is negative 1. So that's going to become plus 9 on the bottom. And so then we just have our last bit of cleanup up top. 6 plus 21 is 27 plus 11i all over 1 plus 9 is 10. Now, if I could divide everything here by 2 or by 3 or something like that, then I'd be able to reduce a little bit. But in this case, there's no reducing possible. This problem is simplified. But the whole point of this exercise was to make sure that we eliminated the I from the denominator, and so we did that by using that conjugate pair.